This is the key for homework 3. First question asks us to assign the configuration for the chirality centers. I see 3 chirality centers here. This carbon has 2 methyls on it, so it is not a chirality center. So assigning priority, fluorine, bromine, methyl, or the rest of the molecule, the bromine is highest priority, fluorine is 2, then we have these 2 carbon groups, methyl is 3, the rest of the molecule is 4. And in this case we see that our 4th priority group is in the plane of the page, so we need to probably do the double switch type of analysis here, and we can do that by redrawing a chiral center without any groups on it. I'm going to switch 4 and 2. That puts the 4 in the back, and I'm going to switch 1 and 3 because the double switch gives me the same chirality as I had before, the same stereocenter as I had before. If I do a single switch, say just 4 and 2, I have the enantiomer. So now I have the same stereocenter as I had before, and this is S. So that's an S stereocenter. The next one, containing the cyanide group, we need to assign priority. The cyanide is number 1. Let's use a different color here. Cyanide's number 1. Then I have these 2 carbons, and the right one has bonds to 2 carbons. The left one has bonds only to 1 carbon, so those are my priorities there. The hydrogen, of course, is on the wedge. So if I count 1, 2, 3, I get a counterclockwise direction, but the hydrogen is in the opposite position that we want, so this is R. And lastly, let's use a third color here. We want to look at this chirality center. And so I have a carbon attached to a cyanide and another carbon. I have a carbon attached to only 1 carbon, and I have a carbon attached to 2 carbons. So of these 3 green dots, priority 1 is on the lower left, priority 2 on the lower right, priority 3 on the ethyl, and of course the hydrogen that is going back into the page is priority 4. So counting this way, this is S. So I have S, R, S for my chirality centers here. So here I have a pseudoephedrine has an optical rotation. This probably should be a specific rotation. I misspoke or mistyped here. Specific rotation of 52, and I have a solution of the negative, the minus enantiomer in ethanol with an observed rotation of 31.2 and a path length of 2 decimeters, concentration of 0.6. And so when I do that math, I think we end up with 26 degrees. If I want to calculate the percent EE, 26 over 52, and that equals 50% EE. Now, what is the enantiomer that's present in the greater amount? We have, obviously this is a negative rotation, so the negative enantiomer is present in the larger amount, and so this is 50% EE of the minus enantiomer. Question 3. Identify the following pairs of compounds from these 5 choices. We've seen this before. The important thing here is to recognize that the alkene is in different spots, and so that means that we have different connectivity. Even though we have 6 carbons in a ring with 2 methyls, you might say that the methyls could be in different spots relative to the alkene, if that helps you, right? So if I had that green methyl there instead of this one, then I'd have the same compounds, but I don't. So I need to erase the green stuff and observe that I have constitutional isomers here. No matter which way you look at it, the connectivity is different. For the second one, I have what appears to be 2 stereocenters, and we can assign priority here. If I want to look at this one, the carbon containing the CN is number 1, the isopropyl is number 2, the methyl is number 3. counting in a counterclockwise fashion, that gives me S, but of course my hydrogen is in the forward position, so this is an R stereocenter. This one's the same configuration over here. And then if I want to consider, I'll give this a red dot. What is the stereochemistry here? Well, the CN is first, the rest of the molecule is second, the ethyl is third, and the hydrogen that is coming towards us is fourth. So again, counting 1, 2, 3, that gives me counterclockwise. That is also R. I'm going to erase the hydrogen so I can put an R there. So this one's R. If we want to look over here, we've already assigned priority, so this is easy to do. And the hydrogen's in the correct spot, so this is also R. So these look like they are identical. These two molecules are identical. They're connected the same, they have the same formula, and as we've established, they are both the RR stereoisomer of this compound. Here we're asked to draw mechanistic arrows and label each step. So here we have what appears to be a rearrangement. The cation is secondary right here, it's tertiary right here. So we need to draw this hydrogen and use it properly. Make sure that your arrow comes from the CH bond and is pointed directly at the cation. There's no other way to draw this rearrangement. So if you have an arrow coming off the hydrogen, or if you have the cation moving like this, those are incorrect. So do not draw those arrows. These are not correct. And then the last step is simply nucleophilic attack. So here's rearrangement, here's the nucleophilic attack. So this is maybe the second half of a SN1 type substitution. Here we have a slightly different mechanism. So we're obviously making this bond here, the OC bond, and we're breaking one of these CO double bonds. And that's going to get us to here. So this is nucleophilic attack. In this case, it uses two arrows. If you want to think about how this happens in two arrows, well, we might ask you, draw me the resonance structure of this compound. There's a carbon with an oxygen double bond. The only resonance structure we know is this arrow. And that gets us to this structure. And you'll notice that if I drew an arrow from my ethoxide, I could draw it just like that to get to the second structure over here. So if you're stuck on a mechanism, you don't know where to go, sometimes drawing the resonance structure can help us decide how to proceed. And you'll notice that the arrow that I used in the resonance structure right here also appeared in my two-arrow mechanistic step. That's the same arrow. So that was nucleophilic attack, and then we observe that the chlorine is free. It is lost. So it is the leaving group. You can lose it like that, and we reform the CO double bond. I'm going to erase a couple of these extra arrows here. They're getting confusing. We don't want this arrow here. So now these two arrow pushes help us to assign loss of leaving group as our arrow pushing pattern for 4B. Moving on to 5, modify this diagram to show the effect of adding a catalyst to the reaction. And so we know that the catalyst will speed up the reaction, it will lower the EA, so really all you have to do is give me something that has a lower hump, a lower hill. And is the original reaction exergonic or endergonic? Well, we aren't changing this distance no matter what we do to that EA, to the energy. So this is exergonic. We're giving off energy as we go from reactants to products. Excuse me. Number 6. The rate law for this reaction down here is rate equals K times the cyanide concentration times the propyl chloride concentration. So if this were doubled, the rate would double because this has a 1 here, this has a 1. So if I use twice as much stuff right here, I have twice as much rate. If propyl chloride were tripled, rate would triple. It's as simple as that. If these were second order effects, then we'd have to use the square. But these are both, they're both first order in cyanide and first order in propyl chloride. And then we want to draw mechanistic arrows to show the flow of electrons. And if you haven't figured this out already, this is a SN2 reaction. This is a nucleophilic attack and loss of leaving group in the same step, so this is SN2 type arrow pushing pattern. We saw a lot of these this week in class. Moving on to number 7. Determine the delta H for this reaction. Use table 6.1 to look up some BDEs. So we want to do bonds broken minus bonds formed. So what bonds are broken? This bond is broken. What bond is formed? That bond is formed. So here we're only going to have 2 numbers. So I need to look up a CH2 to bromine, and I find that in the middle of this chart towards the bottom, 285. And formed, I need to look up a CH2 to OH, that's 381. And broken minus formed, 285 minus 381, 285 minus 381, negative 96 kilojoules per mole. Alright, so here we're asked to predict the sign of delta S. So there's no math to do here, we just want to observe really what's happening. So you could think of it as A plus B goes to C, D, and E. So in this case we're combining 2 molecules and we're getting 3. So we're increasing the randomness, we're increasing the entropy. We expect a positive delta S in this case. And here we have an alkene, we have water, and if you're observant, you'll observe that here's our water that we've added to the alkene. That's a topic for chapter 9. We don't need to know how this reaction proceeds. We just need to observe that essentially A and B produce C. So we've taken 2 molecules, created 1. We have a negative delta S here. We've reduced the entropy in this case. We've reduced the randomness.